Hello, I'm Gil Carlson, Director of Technical Services for ITT Fluid Handling Division. In this section, we shall discuss the use of pumps as flow indicators. Many applications of pumps and their usage as flow indicators establish an unrealistic estimation of flow from that pump. We shall try to define the overall correction factors that should be applied to the pump curve in order to establish as accurate an estimation of flow as possible. One of the important things about the use of pumps as flow indicators, and indeed is correlated with the use of flow meters as flow indicators, is to provide an accurate estimation of head, because it is head difference that we utilize in terms of these estimation practices. For example, we can have a pump curve illustrated as thus, and this pump curve does not correlate directly with the flow meter curve because the pump curve decreases in head basically as flow increases. To the contrary, a flow meter curve increases in head difference as flow increases. Now the problem is this, that because of the difference in the shape of the head curves, if this were the true head estimate, and we have done everything correctly, we will reach the same assessment for flow through the pump curve as well as through the flow meter curve. On the other hand, should we estimate the head as being less than that which is actually occurring, our wrong estimate will establish less than required flow through the flow meter, but more than required flow through the pump curve. Now then, how do we estimate as to pump head, and what are the problems corresponding to this estimation? It will be remembered that head has a meaning of foot-pounds of energy per pound of liquid. We cancel this out, we're left with the term foot head. Foot head is a generalized term applying to both the flow meter curve and to the pump curve. Now, the pump curve and the flow meter curve will register as to foot head of fluid being pumped. And what this really means is that if we have a large amount of air in the water, this will reduce the density of the water, and because of the reduction of density, the pump curve and the flow meter curve not being aware of this change in density, will still register to the fluid being pumped. The problem here is that to establish foot head, we must take our readings in terms of delta PSI across the pump and or across the flow meter. If we incorrectly assess the conversion from PSI to feet head, we will establish the problems illustrated on this slide, in which an incorrect assessment of head establishes less than required flow through the flow meter, but more than required flow through the pump itself. Now, the density of liquid is affected by air and will also be affected by water temperature in terms of the conversion. So we have established for various fluid-specific gravities and for various water temperatures as to the conversion factor that should be used in converting PSI over to foot head. we employ the correct density correction factor or conversion factor, we will establish a close correlation of head with, in terms of correctness, with the pump curve and the flow meter curve. Now, given that we have a finally adjusted pump curve, adjusted as per the later descriptions, we can take and utilize the foot head reading to intersection with that finally adjusted curve to determine the flow rate through the pump. In order to accomplish this, however, and to make sure that the final pump curve is as we believe it to be, we must establish that the pump impeller diameter curve is that which we believe it to be. And what we would do then is to take the pump, utilize the discharge shutoff valve, and shut the valve off, reading the differential pressure occurring across the pump itself. We do this with a single gauge to make sure that we have no calibration difficulties with the gauge itself, and by opening and closing either side of the pump to the gauge, we can read the differential pressure. We would convert this to feet of head and compare this to the curve which we believe to be true, but make sure that the impeller diameter comes to the same shutoff head that is established by the published curve. If it is different, we would adjust the curve to the impeller diameter that is actually installed in the pump and draw a curve parallel to the published curve in order to use this as the base for our consideration. Now again, to emphasize, we should use for the pump a single gauge connected to pump suction and to pump suction and to pump discharge, these points being valved off so that we can open the valve to discharge pressure, read the gauge at that point, close the valve then, open the valve to suction pressure, read the gauge, and subtract the difference. This will give us the foot head after we have correlated this with the gauge readout in terms of PSI to the proper conversion in terms of conversion of PSI to foot head. This also illustrates a connection to a strainer connected to the pump suction, and we can utilize these gauges also to determine pressure drop through that suction strainer on a continuing basis to ensure that the strainer does not become clogged. Now, another important point has to do with this. That the published pump curve is a curve that illustrates the total energy head delivered by that pump to the system. And if the pumps are square, that is to say, the suction pump size is equal to discharge pump size, we will need no correction other than that which was previously illustrated, where we did check as to impeller diameter. However, many pumps, especially the larger ones, have a suction size which is larger than discharge size. And this means that we have a velocity head correction, because velocity heads are different from suction to discharge and must be corrected for if we are to use gauges as at the pump suction and discharge flanges. Now, The correction then is this, that the published curve is illustrated by the upper curve shown here. The velocity head difference, however, means that with a suction size larger than discharge, we must correct for that velocity head and correct the curve to a lower illustration in terms of readout for flow estimation purposes. And this can be accomplished very simply, because we do have correction curves that would allow for us to do that. And this particular illustration is for a pump which has a 2-inch discharge by 2.5-inch suction size. And what we do is we take at any flow point registered to various head differences and subtract that head difference to establish the corrected velocity head curve. This is accomplished by the use of velocity head correction tables. Such a table, available from Bell and Gossett representatives, is shown here, in which various degrees of velocity head correction, that is to say 1/2 foot, 1 foot, 2 foot, 3 foot, 4 foot, 5 foot, etc., are correlated with the gallon per minute flow rate necessary to cause that velocity head correction. In this circumstance, we're dealing with a pump which has a 2-inch discharge and a 2.5-inch suction, so that for 1/2 foot correction, we are dealing with 72 gallons per minute. For a 2-foot correction, we are dealing with 165 gallons per minute flow rate. For a 4-foot correction, we are dealing with 230 GPM. And for a 6-foot head correction, to the order of value higher than that. Now we can take then the basic curve and illustrate those velocity head corrections so that we finally establish the final velocity head corrected pump curve. And we can then use that pump curve, corrected, remember, for impeller diameter, making sure that we have utilized the correct PSI to foot head correction, and having corrected the curve to velocity head, we can use this with a degree of assurance that the flow rate established from that finally adjusted curve is indeed the flow rate being passed by the pump.